Welcome back. We have an exciting presentation for you with Genoa Solutions. Please welcome your presenters, Augusto, Ricardo, and Patrick. Welcome, everybody.
Hi. I think it's just me.
Hello, Augusto. Okay, nobody else?
Yeah, just me.
Okay, go ahead.
Okay, thank you, everyone. Good morning, good afternoon, or good evening. My name is Augusto Pereira. I'm from Genoa. The authors are me, Ricardo Pereira, and Patrick Silva. They are from Vale. This presentation is a result of a project we developed with Vale, as you can see here in the map. It's a project of two coal mines located here in Mozambique. Moatize, it's the place. This is actually the second project in a row we have developed together. The first one, we have modeled the entire supply chain from the mines, passing through the railway, and modeling also the port, so it was an integrated system. And in this one, we are modeling in detail the mines here, so the frontiers are a little bit different. So here we have a brief description of the problem. We studied two open pit mines. They are coal mines located in Moatize, Mozambique. And each of the mines contains several mining fronts from where many variety of coal, we name plies, can be retrieved. They are retrieved by trucks and moved to the proper destinations. The coal can be moved to the crusher or to the ROM pad. The ROM pad is a buffer that is located right next to the crusher. And there is another material that can be moved from the mining fronts, that it's the waste. And the waste is moved also by trucks to a proper location. It's like a deposit of waste. After the crusher, the coal go to the crusher, they are processed in plants, and three products are generated: thermal metallurgical coal and a subproduct we call tailings. The tailings are moved to a silo by conveyor, and from the silo they need to be moved to a dam, also by truck. The trucks need to empty those silos. They cannot be full because all the system would stop. I'm gonna have a diagram later, so it's gonna be clear. Besides, we need to consider the shifts of the operators that works on the trucks and on the loading equipment. Besides, all the equipment involved, trucks, loading equipment, and crusher, are subjected to maintenance and failures. In this diagram, I think it's going to be easier to understand the problem. We have several mining fronts here, from where the plies or the varieties of coal are retrieved, and also the waste is retrieved from here. Then they travel by truck to the crusher or to the ROM pad, and if the truck is moving waste, he's gonna let the waste in the deposit. In general, they let the coal in this buffer when the queue in the crusher is too big, or there's a problem, a failure of the crusher, something like that. So this is a buffer, and physically it's very close to the crusher. From here, the coal goes to the plant, is processed. The resulting coal, the processed coal, is stored here in the yards, but this is out of scope of our presentation. But we need to mine the tailings that goes to this silo, and also needs to be emptied by trucks, and the trucks need to take these tailings to the dam. This truck here belongs to the same fleet of trucks that move the coal, so it's all interconnected. That's why you need to consider it in one single problem. And just to have a notion of the complexity and the numbers involved, we have 2 mining sites, and in total we have 8 mining fronts, 1 loading equipment per mining front, about 80 trucks of different fleets, and the fleets are different from one another by the capacity, the speeds, and the failure profile. We have a dozen of different plies, and we have 1 ROM pad, 1 crusher, and 1 tailings silos each mine. So let's talk a little bit about our solution. Well, we address this problem by developing an optimization model and a simulation model. The optimization model was implemented using the CLP solver. It's a free solver, and it was embedded in the AnyLogic, so we could use the outputs of the optimization model as inputs to the simulation model. The objective of this optimization model is to maximize the transportation capacity by sizing the truck's fleet for each mining campaign, and also allocating the volumes of coal, tailings, and waste to be transported by each fleet. And the simulation model was developed using AnyLogic and allows the graphical and temporal visualization of the results provided by the optimizer. Moreover, it allows the following analysis. We can analyze uncertainties like equipment failures. We can analyze cycle or transit times of trucks, travel, queues, loading and unloading times in the crusher and in the loading zones. We can analyze the utilization level of the trucks, the loading equipments, and the crusher, the input rate on the crusher, which is the mine throughput, and it's possibly the most important KPI of the mines. And we can also analyze and evaluate different scenarios of shift planning for the operators and different plannings for maintenance schedules. Here we can see briefly the mathematical formulation of the problem. The objective function, as I mentioned, is to maximize the transported material, and we have certain constraints here. First one, we need to meet the crusher demand. We need to ensure the mass balance in the ROM pads. We have to meet the required volume of coal and waste to be taken from the mining front. We need to mind the time availability of the trucks. This is related to the capacity of the trucks and to the, it's related to the number of trucks of each fleet and to the time horizon of the problem. We have also the capacity of the trucks and the mass balance in the other nodes of the problem. And well, why AnyLogic? For basically 3 reasons. First of all, because it was important to use an optimizer, and it would make it very easy to import this optimizer to AnyLogic. So we could easily import an external Java library, in this case was the CLP optimization package, and bring it to the model. Besides talking about the simulation, we have certain aspects that should be modeled as agents using, for example, state charts, and other aspects that should be modeled as discrete event simulation. For example, the behavior and the traveling of the trucks could be easily modeled with state charts as like agent-based simulation, because the trucks can be idle, they can be traveling, they can be loading or unloading. So it's like a classical problem to use agent-based modeling. But when the trucks reach the final points of their route, we need to then care about queues, resources, seizing the resources, and things like that. So it's a classic situation to use discrete event simulation model. So when the trucks are in the crusher or in the silo or in the mining fronts, it's easy to model it using discrete event blocks, as you can see here. So now I have some videos about the model. So you can see the trucks moving throughout the mine. Here you can see the mining fronts. Can I pause it? I'd like to pause it. Here you can see the mining fronts. The black trucks are full. The gray ones are empty. So here we have the crusher, the ROM pad. They are very close to each other in real life. Here we have the waste deposits, the tailings silo. These trucks are emptying the silo in this route here. This is the dam right now here. Here we have the crusher, the logics in the crusher. Here we have the trucks in line here. They will unload in one of the hoppers here. Have the lines here, the trucks here. You can see that the trucks never unload in parallel. They always unload one at a time. And because Vale thinks it's a little bit dangerous for 2 trucks to maneuver at the same time, so they do not unload 2 trucks in parallel. But the model allows them to test this possibility in a safe environment. It's flexible at this point. So it's one of the things the model allows them to do. Here we have a dashboard of the crusher, but I'm gonna talk more about this in a moment. Here we have the operation of the trucks in the mining fronts. They are forming a queue here. Here they are loading in the loading machines. Here you can see the stocks available in this mining front. We have the waste. These two first are the waste. The second ones are the plies available for the trucks to move. Here it's just a print screen of the output of the optimizer. So we have the amount of material moved from one origin to one specific destination of each one of the plies. Here it's the total amount in tons of material that it would be moved along the time horizon, the studied horizon. Here we can see a dashboard with the main KPIs of the crusher. So we can see the average queue time, both in time, in minutes, this one, and the average queue in number of trucks. Here we can see the utilization level of the crusher. Here we can see the average rate in tons per hour. And here in green and in red, we can see the hour rate in tons per hour. Here we can see the rhythm of trucks in trucks per hour arriving to the crusher. And down here, we have the average travel distance of the trucks. The average one in blue and the one in the last hour in the yellow one. Here we have the main KPIs of the mining front. We have the availability and the utilization of the loading equipment. We have its productivity in tons per hour. We have also the queues, just like we had on the crusher. And here the stocks, as I mentioned earlier, the waste stocks and the plies available for the trucks to move. Here we have the timeline of the trucks. They can be idle. Each one of these is one truck. They can be idle, traveling, loading, or unloading. They can be in failure too. This is in red here. Here we simply have the loading equipment timeline. It's very similar to the trucks. It can be loading, the truck can be idle or in failure too. And that would be it. I'm gonna go through the conclusions, then I will try to run the videos again. This is a optimization and a simulation model we developed for Vale to use in a coal mine located in Moatize. The optimization model aims to size the truck fleet to be used and maximize the amount of coal to be transported, respecting constraints regarding the transportation of waste and tailings. The simulation models allows temporal visualization of the mining operation and includes uncertainties such as the failures, which are very important. The model can be used to compare the mine throughput in different scenarios, as well as to analyze the mine behavior with different truck and loading equipment fleets, simulate different shifts and maintenance policies. And in a future project, there are some aspects we could improve. For example, we could try to use Cplex or Gurobi instead of the CLP solver, because they are commercial solver and possibly would perform better. And for that, we could maybe use Python pipeline. We are modeling two mines in a static way, but we could, if we model the mines as an agent population, for example, we could model then a flexible and scalable number of mines at the same time. And another great improvement we could incorporate, it's that the movement of the trucks, we made it in a schematic way, but we could use the realistic roads, the realistic paths, so we could also see bottlenecks in the mine, not just average transit times. So it would be better. It would be a great improvement for the project. That's it. The team, it's me, Augusto Pereira, Karen Kimura, Jonathan Carvalho, Renata Rodrigues from Genoa, and Afonso Medina, that was the coordinator of the project. And in Vale, we have Ricardo Pereira and Patrick Silva that help us a lot. Thank you very much for your attention, and I'm sorry for the problem with the video. I should have tried earlier in the presentation mode, but thank you anyway. Well, I have a few questions here. Is the process weather sensible? Well, I think the production of the mine may change over the year due to weather conditions, and this would reflect in rates of the equipment, in possibly the transit time of the trucks, and the model is flexible at this point. So through the input interface, the user can change all these parameters and represent this changes caused by the bad weather conditions. For example, too much rain, I guess, possibly it's going to slow down the mine operation. Did you use other libraries besides process modeling? Have you considered to use material handling library transporters to model trucks as well? Well, actually, we haven't. We didn't think about it. I mean, the process modeling libraries served us well, but of course it's a possibility, and we are gonna write it down to a possible future project. Maybe these libraries would help us in some aspects. What are the improvement in percentage of trucks productivity compared to the baseline? Well, we didn't test that because once we finished the model, we have a validated scenario that is representing the reality. But now they are testing, they are working with other scenarios. But so I don't have this number just yet. How did you make the trucks respect the solution from the PPL? Is the cargo ready to move at the start of simulation, or these values changes on time? Well, all the cargo is available in the beginning, and the optimizer gives the optimal solution for each campaign on the crusher. So we need to enforce these sequences because the optimizer doesn't have that. But the cargo, yes, it's available right at the beginning. Did you consider other simulation platforms other than AnyLogic? Actually, in this project, no, because as I said, this is a second project, and the mine is, there are a lot of products and platforms for mining simulation, but this model integrates with the rail and with the port models. So we consider AnyLogic because it would be also connected. It's a very large model, and we can switch on and off each part of the system. Are Vale Genoa considered to model to optimize the core movements in the future? I'm sorry, I didn't think I get that. Are Vale and Genoa considered to model to optimize the core movements in the future? I'm sorry, didn't understand. Yes, please. Yes, we are already doing that. We optimize the routes, the truck fleet, and then we simulate no problem. And then we simulate the coal mine, this phase, and then we also simulate the other parts of the supply chain, the processing in the plants, the stockyards, the rail expedition, the railway itself, and the port in Nacala, which is in the coast. Movement using at the moment, no. 7.1, I don't think so. It's a possibility. We need to study that. but at present, I couldn't say. Did you consider the changes of the mine layout, the changement of qual front in your model? Yes, this is flexible. We can change that in the interface. It's an Excel interface, so you can put all the mining fronts you have, and the model is flexible. Both the optimizer and the simulation flexible at this point. So you can add more or remove mining fronts, add more roam pads in parallel, that the model will be built automatically. Was truck breakdown a factor? Yes, the failures of the trucks were considered, as well as the failures of the loading machines, and they are very important because it's very uncertain, and the optimizer cannot include that. And for reality, for model validation, it's very important to include this factor. Okay, thank you.
Okay, thank you so much, Augusto. Very good presentation, and we will be seeing you soon. Thanks again.
Thank you.